continue now with a talk by Jeremy Vicary, who's going to speak about the categorical framework for the quantum harmonic oscillator.
Hello, and thanks very much to the organisers for this chance to speak to you. And I've been really enjoying meeting so many people that I've wanted to meet for a long time, and suddenly they're in one room and it's very easy to talk to everybody, which is great, and I hope this happens lots more in the future. Okay, so I'm going to talk about a categorical framework for the quantum harmonic oscillator, and this really derives from the work of Samson Abramsky and Bob Coker and Ross Duncan, sort of the second session that we had today. That's really a completely abstract framework for quantum mechanics, and they've described how you can do lots of things in that framework that you would want to do normally, like talk about states and entanglement and superposition and things like that. But there's a lot more that we like to do with quantum mechanics, which is construct state spaces for what we think are actual physical systems and manipulate them and understand how those state spaces relate to the actual physical system. And because it's very difficult to know how to do that if you lack the conventional Hilbert space framework, so in sort of basic quantum mechanics, one of the most straightforward ways of creating a state space and talking about evolution and things like this using the Schrödinger equation. But if you haven't even got the complex numbers as your scalars or anything like that, how can you even start to formulate your quantum mechanical models in that sort of way? So I'm going to talk about a different, inherently categorical way to talk about the quantum harmonic oscillator, which is one of the most fundamental quantum systems, I suppose. Okay, so this is an overview of what I'm going to talk about. I'm going to give brief introductions to categorical quantum mechanics and to the quantum harmonic oscillator. And then I'm going to talk about how the state space can be constructed categorically. That's symmetric Fock space. And I'm going to introduce a graphical representation so that we can just draw pictures of everything to prove all of our theorems, which everyone here likes to do so much, so that's great. And then I'm going to get specific and show how you can construct raising and lowering operators, show how you can demonstrate that the canonical commutation relations hold, which are the sort of one of the central non-trivial aspects to the mathematics of the conventional quantum harmonic oscillator. I'm going to talk about coherent states and also about exponentials, which strangely seem to emerge. Then I'm going to talk about actually doing this with real Hilbert spaces, which obviously is the motivation. And then if we've got time, I'll talk about more sort of exotic Fock spaces, because although the inspiration for this just comes from conventional symmetric or antisymmetric Fock space, once you've got this abstract categorical formulation, you can put it to work in lots of completely different categories, and you get new and interesting things out. And then finally, I'm going to ask, where does the quantumness really come from? If we start from what is effectively just a category with linear structure, how are we able to get out things like the canonical commutation relations, which are often seen as really the hallmark of quantum behavior? Okay, so I can do this very quickly because we've already seen this a few times today. So I'm basically going to work in a symmetric monoidal dagger category, which I'll call C in general, and I'm going to assume that has dagger biproducts. And dagger biproducts just mean that you have binary products and coproducts which coincide in the category, and that are injections and projections from those products and coproducts are related by the dagger, and they're sort of nicely normalized. So I'm not going to worry about duals too much, and there are interesting reasons for that. Duals tend to conflict with infinite dimensionality, because if you have infinite dimensionality, then you can use the duals to sort of count to infinity. But it's very difficult to add infinity to a ring like, for example, the complex numbers. So we're not going to, this category C that you keep in your mind, you shouldn't imagine that that necessarily has duals, but otherwise it has all of the other structure that we've talked about. Okay, so here's an equally fast introduction to the quantum harmonic oscillator. All that the quantum harmonic oscillator is traditionally is the solution to the Schrödinger equation for a single particle in n dimensions operating in a quadratic potential. And every undergraduate physicist hopefully will do this, and they'll find that the state space is symmetric Fock space, which has this weird structure of a direct sum of lots of subspaces. And each subspace, separated by the direct sums, can be interpreted as having a definite number of excitations. So it's not like classical physics where your ball rolling in some sort of dip can have a sort of continuous, definite energy. Rather, our system is sort of quantized, which is, of course, a hallmark for a constrained quantum system. And the state space splits in exactly this way. And we talk about the subspaces. I'm afraid I haven't got a pointer, so I'll have to use my finger. I don't think that's a very good idea. It'll probably break something. So, so we talk about the subspaces as having a fixed number of excitations, and we might even loosely refer to those excitations as being particles, because when we use this mathematical formalism for quantum field theory, they do describe particles in the sort of free quantum field theory setting. But we're not worrying too much about whether we're really doing quantum field theory here. We're just examining how we can get the Fock-space mathematics out of the category theory. Okay, so one of the most important tools to have in your toolkit when you're dealing with the quantum harmonic oscillator, the raising and lowering operators. So these are operators from the Fock space onto the Fock space. So they take a state of Fock space, they give you back another state of Fock space. The first one, the A phi, that's the lowering operator. And that takes a parameter phi, which is a state in your single particle space. Your single particle space typically is just a finite dimensional Hilbert space. Let's keep everything finite dimensional to keep it simple. It's just a state in your single particle Hilbert space A is just a finite dimensional Hilbert space with n dimensions, where n was the number of dimensions at the top, which is the space that your particle is moving in. So what we do is we choose a particular phi, which is like choosing a direction in this n-dimensional space, and then the lowering operator A phi removes an excitation in that direction. If there was no excitation there in that direction to begin with, it will completely annihilate the state. But if there was one, then it'll just sort of take that away and you'll still get something non-zero. So A phi dagger doesn't do the opposite, but it does the adjoint operation. It's the adjoint operator mathematically. It will add an excitation in this particular direction phi. And they should satisfy these very well-known, very famous canonical commutation relations, which relate to what should happen if you put in two different excitations with the raising operator, or remove two different excitations with the lowering operator, or if you add and remove in sort of the opposite order. So those really are the hallmark of symmetric Fock space and of the quantum harmonic oscillator, and so getting that out will be one of the most important results. So one of the things that you immediately note, perhaps if you're a pure mathematician looking at that structure of symmetric Fock space up there at the top, is that it carries a sort of obvious commutative monoid structure. And what that means is that if you take two pure states, and what I mean by that is states entirely in one of the direct sum segments. So let's say you take a 2-particle state and a 3-particle state. There's an obvious way to combine them to create a 5-particle state. And that gives you a monoid structure. And that's that's commutative exactly because our n-particle subspaces were formed by symmetric subspaces of the full tensor product. And this was originally noticed by people who are very aware of category theory back in 1994. But all of the results that so they certainly noticed this symmetric Fock space structure was a commutative monoid. But all of the results that we present here will be new results, but very much inspired by their work. And the final interesting mathematical fact to notice is that Fock space, symmetric Fock space, satisfies this very nice, very sort of categorical identity, which sort of says that it takes direct sums to tensor products. Okay, so what is a commutative monoid? Well, we've seen these lots today. This is how I'm going to draw them in this talk. If I have a commutative monoid on A, then and with multiplication G and unit U, then I'll write AGU, and I'll write plus to denote the fact that those three make up a monoid, because use plus because products in category theory give you monoids for free, so that's the notation. And the category itself of commutative monoids is going to be very important, and it's got initial object, it's got terminal object, it's very well behaved, but we won't worry about that too much. Okay, so here's the reason that we're all here, I suppose. How do we define our quantum system in this categorical way? So we do it algebraically. We take our category C, and then we consider our category of commutative comonoids. So I've now replaced the plus by an X, which just means that it's the category of comonoids, not the category of monoids. And I'm going to consider a particular adjunction between the free comonoid functor and the forgetful functor, which takes a comonoid and forgets the co-multiplication and co-unit and just gives you the underlying space. And I'm going to define the composition of Q followed by R to be the Fock space comonad. And it's a comonad because of the way around that the adjunction is going. And along with the comonad will come unit and co-unit morphisms, which I'll call epsilon and eta. And I'm going to define the image of a particular object A and C. If you act on that with Q, you get a comonoid, and that comonoid has got co-multiplication co-unit morphisms, and I'm going to define those to be dA and EA so that I can refer to them. So in fact, just by setting up this structure, we've instantly got 4 natural transformations kicking around. We've got these dA and EA are stages of natural transformations which form co-multiplication and co-deletion, and they in fact are stages of natural transformations. And we've obviously got the epsilon and eta, which form the unit and co-unit for the adjunction. And we'll see that the behavior of epsilon is to project out the single particle subspace of the Fock space, and the E natural transformation projects out the 0 particle subspace. So the epsilon was the sort of the second factor in the direct sum expansion, and the 0 particle space was the first factor. So the question is what to do with this dagger that's so important. This C, of course, is a dagger category. It has this endofunctor on it, which somehow abstractly represents the ability to take inner products. And the answer is we're going to ask that everything, almost everything that we can possibly get our hands on, be compatible with this dagger. So we're increasing order of importance. We're going to say first that the comonad F on C commutes with the comonad dagger on C. So that's fair enough. We're also going to ask that epsilon be normalized. Epsilon, as we saw, is a projector. So we can say that, and we can turn this projector around by using our dagger. So we can say if we start with A, and we apply epsilon dagger to get to FA, then we apply epsilon to get back to A again, we should just have the identity. So we're going to require that. And lastly, the most important is that we're going to require that the products are preserved unitarily. So we'll take a closer look at that because that's the most important part. Because Q is a right adjoint, it must preserve limits, and in particular it must preserve the byproducts. It must take product to product. Product in C is given by byproduct, and product in CX is given by the tensor product of the underlying commutative comonoids. And so, by the very fact of having an adjunction, we'll necessarily have these unique natural isomorphisms. And I'm going to require that these isomorphisms be unitary. In other words, that their adjoint, their dagger, is their inverse. But I can't do that directly because dagger doesn't operate on CX. It operates on C, the underlying category. But I've got this forgetful functor that I've used. So I can apply my forgetful functor to bring these natural isomorphisms back into C. And then I'm going to require that those natural isomorphisms be unitary. So that's my setup. And something that some people immediately say when they see this is, but your forgetful functor is unique, and so your right adjoint is unique, so either it's going to work and it doesn't, and probably it doesn't work. Well, but of course, right adjoints are only unique up to isomorphism, and certainly not only unique up to unitary isomorphism. There'll be many right adjoints which don't give this sort of unitary dagger preserving structure, and there'll be plenty of other right adjoints which will give the correct structure. Okay. So now, what are our graphical representations? So this is stuff that we've all seen before, at least outside of the Fock space context. If I just have a sort of vertical line with dots around it, that's going to be just the identity on my Fock space. And I'm representing my Fock space by these funny sort of dotted lines down the outside. They represent sort of being encapsulated by the Fock space endofunctor. You can think of it like that. And so, of course, these dotted lines must be functorial and must satisfy the diagram in the top right. And I'm going to represent my co-multiplication and my co-unit by these sort of typical splitting and deleting operations that we've seen before. But of course, everything is encased by these dashed lines because we're working with Fock spaces. So that's half the graphical representation. Here's the other half of it. Now we need to look at the epsilon, the eta natural transformations, see how we're going to represent those. Epsilon takes Fock space and then just spits out the original single particle space. So I'll represent that just by stopping the dashed lines. So that's very straightforward. And then if we look at the naturality equations for epsilon, we see that they're very natural in this context. The naturality conditions are simply that you can sort of pull back the dotted lines and apply epsilon either after applying this operation f or before, but that's clearly topologically just like saying that these ends of the Fock space functor are like free ends and we can just pull them back to sort of behind the operation f. So we can deal with that very easily. And eta is our final natural transformation that we require a picture for. So I'm going to use a sort of double line for that. And now we can see what our adjunction equations, which obviously epsilon need to satisfy, look like. And that's what they are. And we'll find that they're going to be key for proving our theorems about the quantum harmonic oscillator. OK, so here's a lot of emergent identities that come out. The most important identity that comes out is that the co-multiplication D on the Fock space, in fact, forms a bialgebra. And that comes fundamentally from the fact that the Fock space operation is taking the linear structure into the tensor product structure, and if you have a byproduct, then the multiplication and co-multiplication on that byproduct necessarily has a bialgebra property, and that's going to be very important. You also get this rather neat identity in the top right that says if you combine two Fock spaces and then just select out a single particle, that's either the same as selecting a single particle from the first and selecting nothing from the second, or selecting the single particle from the other Fock space. So that's sort of quite intuitive. And we're also going to get these three other properties. The first property is that this epsilon is normalized. So if you've got two free ends of these dashed Fock space lines, you can just get rid of them. But actually we cheated because that was our second requirement when we wrote down the definition of our right adjoint Q. But we also get out these other normalization conditions that do really come for free and that we haven't cheated by requiring explicitly. So they're quite nice. So okay, so now what are the raising and lowering operators that are so important? Well, we apply the raising operator by taking some state phi, which is represented in the usual way as a sort of line that appears from nothing. We're going to embed it into the single particle sector of our Fock space. And then we're going to take these two Fock spaces. We've got our new Fock space that just contains a single particle excitation. And we've got our original Fock space. And we're going to use our multiplication operation to combine them together. And that's what the raising morphism is. And that's, I suppose, reasonably intuitive, I think. And the lowering morphism is, of course, just the adjoint operation. And so you can get that just by flipping the diagram on a vertical axis, but on a horizontal axis, but keeping the arrows pointing in the same direction. And so what's happening there is we're taking Fock space, we're sort of splitting the particle content into two. And then on one of the branches, we're projecting out to the single particle subspace. And then we're taking the inner product with our chosen state. And that performs the lowering operation. OK, so what about the canonical commutator? Well, the most straightforward one is when you're going to look at the commutator for two raising operators or two lowering operators. It's just the same thing. So we're going to look at the canonical commutator for two raising operators. And this goes through very easily. First, we apply a raise with psi, and then we raise with phi. But we can use the fact that this multiplication operation is associative to rewrite the multiplication like that. But then, of course, the multiplication is commutative, so we can switch the legs. Then we can use associativity again to put it back into the original form. And then we see that we've achieved exactly what we wanted, which is switching around phi and psi. OK, but sort of less trivial and much more interesting is the non-trivial canonical commutator. And perhaps one of the most interesting things to point out about this is that, firstly, I suppose it's normally written A phi, it's normally written AA dagger minus A dagger A equals whatever, but of course in general we haven't got negative, so we've had to push that over to the other side and hope that it still holds. But the other interesting thing is that we haven't had to worry about domain problems at all. When you normally work with this, when you normally work with the conventional quantum harmonic oscillator in Hilbert spaces, these raising and lowering operators are unbounded operators, so they won't be defined on the entire Hilbert space. And you can't just say that this particular linear combination of unbounded operators equals this particular bounded operator, the identity, because they've got different domains. That doesn't make any sense. So you've got to say, oh, OK, I only want them to be equal on their common domain, and so on. But of course, we can't say any of that, even if we wanted to, category theoretically. So you know, the equation had better be right as naively written or not, and it is right. So I think that shows you some of the power of category theory, that it lets you, as long as you can solve all of your sort of analysis problems straight off the bat, such that you know you've got a well-defined, category, then you know that you're guaranteed to be able to compose your morphisms everywhere, because that's just the axioms of the category. So having hopefully pushed all those questions to the side when we constructed our category, we don't have to worry about domains or not being able to add things together, because we're guaranteed to be able to, if in fact this is a valid category. OK, so very quickly, how do we do this? How do we show this proof? Well, crucial is this epsilon delta dagger identity, which we talked about a bit earlier. So if you write down AA dagger, you get that first picture. And then you use the bialgebra law to take out that multiplication, co-multiplication in the middle. But then we see we've got two instances of our epsilon delta identity. So we put those in and expand out distributively. We end up with 4 terms. 2 of them will be 0. So we're using our normalization rules now. The middle 2 terms are 0 because you've got a single particle subspace up against a 0 particle subspace projector. But the first 2 terms aren't 0, and in fact they simplify to give exactly what we want. So that's proving the result. Similarly, you can construct coherent states using the eta part of the pair of natural transformations. So that's what it looks like. So you're employing your eta natural transformation there, and you can show that these have all the classical properties that we'd hope. You can copy a coherent state, you can delete a coherent state. And of course, most importantly, when you apply a lowering operator to a coherent state, you're left with up to scalar multiplication what you started with. And it's quite nice to see this very simple proof of that fact. So you write down the first expression that we start with, and then we can sort of peel these Fock space legs away from each other, because it's all just co-multiplications. But then we can see, I wish I could point, I'm going to try and gingerly point at the screen now. So this thing here is an application of our eta natural isomorphism, followed by our epsilon up here. But one of the adjunction equations was that is just the identity. So we really are doing category theory here. The adjunction equations are proving to be crucial for what we're doing and letting us prove theorems that we all know and love in physics, which is the whole point of what we're doing, I suppose. I think I'll miss that out, and I'll go on to talk about something a bit prettier. So what about antisymmetric Fock space? The expression that I gave at the beginning, which was that long direct sum expansion of Fock space, that only applies to symmetric Fock space, so the state space of bosons, if you wanted to use deliberately physical language. But what if you want to talk about fermions, for example? They've got a perfectly good Fock space, and you have raising and lowering operation, and everything goes through the same way. And the answer is that you just need to work in the right category for the sort of physics that you want to do. If you want to work with fermions, then you have to have this property that when you switch particles around, the phase changes in the right way. And as long as you're working in the correct category to start with, so you have this sort of fermionic property, you'll get out exactly the Fock space that you want. But then, of course, there are far more categories than just the category of Hilbert spaces and a sort of simple fermionic category like this. There are all sorts of exciting symmetric monoidal categories with sort of crazy tensor product rules, and in lots of these examples, I won't go through this slide in detail because I haven't got time, but in lots of these examples you will be able to create Fock spaces, and you'll have raising and lowering operators and satisfying the right commutation relations, you'll have coherent states and so forth. But they'll be far more colourful than the sort of traditional bosonic or fermionic Fock spaces which we're used to. Okay, so finally I want to come to this, my last sort of non-trivial slide, which I think is one of the most interesting slide, which is where does the quantumness come from? So the general philosophy that we've been using is just to make everything compatible with the dagger everywhere that we can, because this dagger is supposed to be fundamental to the sort of the categorical approach. So that's what we've sort of put in. But fundamentally, the reason that everything's worked, the non-trivial reason, is that linear structure is necessarily a bialgebra. So, and really, if you look at what axioms we actually had to use to prove the non-trivial commutation relation, that really did the lion's share of the work. So in fact, sitting there all along in linear structure that we've been using for a long time has been this fact that linearity forms a bialgebra, and this bialgebra property has filtered through categorically and allowed us to prove these very non-trivial, in the sense that they're very significant, these very significant statements about the quantum harmonic oscillator, and that allowed us to prove these lemmas, which have always been regarded as really the hallmark of quantumness. But it all just came from this bialgebra structure, which has been there all along, and of course will be there generically in any category that has byproducts. Okay, so in summary, I'll just quickly go through everything that I've just told you. So we had a brief introduction, and then we constructed the state space in a categorical way, completely differently to how conventionally you might use the Schrödinger equation. We developed a graphical representation, and then we showed how you can easily write down definitions of raising and lowering operators, and then you juggle things together, and you can prove almost all of the conventional lemmas that you'd like to prove about how they operate. So I have skipped out telling you how we actually shoehorn the category of Hilbert spaces to fit this situation, and it is quite interesting because in general we need to work with unbounded operators, but of course when you compose unbounded operators, that's often not well defined, but of course we need to be able to compose all of our arrows in our category. So it's non-trivial to make sure that you can actually define everything in the right way so that you can have all these unbounded operators, and you can also compose all of your morphisms as you have to in a category. And then we looked at what you can do with this, which is describe conventional Fock spaces and these sort of weird Fock spaces that come out of much more interesting symmetric monoidal categories. And then we looked at where the quantumness came from. Thank you very much.
Your previous slide, where you said that bialgebra gives rise to the non-trivial commutation relations. So non-trivial commutation relations apply to very special kinds of mutually unbounded observables. So you would immediately think that there might be some connection with what Ross was talking about.
Absolutely, yeah.
Although here it's on the bialgebra level, on byproduct level. So
no, that's definitely.
It's interesting, it's not surprising for physicists that you say Coherent States have classical properties, but of course it's always a question how does the classical world arise from the quantum world, and it's very interesting to see that these special states of Fock space have these properties. Is there some relation to these Frobenius algebras that were used in this measurement?
Well, that's a very interesting question, and has, I think, quite an interesting answer. So they really do seem to be two different types of classicality. It's well known it's been studied for a long time in the sort of linear logic community, that if you have a model for linear logic, which basically is just a category of the type C that we've been describing pretty much, and you have a functor on it, which pretty much is just like this Fock space comonad we've been describing, then the Co-Kleisli category for the Co-Kleisli category for this comonad will be Cartesian closed, which is a very classical non-trivial property, and that is very classical, and people like Rick Blut have been yes. So they've been looking at classicality of that sort, looking at these Cartesian closed categories that come out of these sort of quantum linear categories. But there's an interesting fact that if you juggle around some relationships, you can show that a Frobenius bialgebra is necessarily trivial, and in fact must be one-dimensional, zero-dimensional. But the the monoids created by the Fock space functor are necessarily by algebras. So there's no way they can be Frobenius algebras, because then everything would degenerate. So it seems that commutative Frobenius algebras give classicality in this particular way. Commutative bialgebras give classicality, but in a completely different way that can never sort of come together. It's interesting, yeah.
What kind of physical interpretation would you use later?
So I suppose I don't know to what extent it's a physical interpretation, but it lets you take the inner. It lets you take the inner product. That's what it's there for. That's what it does for you. And the inner product is clearly a crucial part of quantum mechanics, and this is clearly a natural, if not the correct way to axiomatize it. I don't know. So what's the physical interpretation of the inner product? I don't really know the answer to that.
But this is not equivalent to the inner product structure.
It is, yeah. If you specify an inner product structure on every object, then you can derive a dagger structure from that, and vice versa.
Have you looked at the vast literature of Jimbo, Dante, and these people who use this vertex operator things? Because that's a same approach, or the Bernstein approach. If you want to construct a representation category out of creations and annihilations, what actually you want to do? You want to construct a Fock space out of this creation annihilation things. Then you get exactly these complicated combinatorial structures and so on. And it would be tremendously nice to have a much more streamlined version, because these papers are essentially unreadable unless you really recompute line by
I don't know if my papers are readable, but well, I've not heard of any of that, so that's very interesting. Yeah, maybe I could.
Physics papers first, then you can read the math papers.
Well, that are hardcore calculations, so they use all these polynomials and this type of things, and if you don't like it, you would like to see the structure behind it, but we don't care about it.
Okay. Any more questions?
So if it's just a braided and unsymmetric, what other?
Well, it doesn't work. And the basic reason that it doesn't work, as far as I can tell, although maybe there's more to say about this than I haven't realized, but if you try and take the symmetric, what you basically need to do to construct these Fock spaces is to take symmetric subspaces of tensor products. So if your symmetry is bosonic, that's fine. If it's fermionic, you just get a -1 factor, that's fine. But if it's just some sort of e to the I alpha, then the equalizer that defines your symmetric subspace is just 0. So it seems that it just doesn't work. The other interesting sort of way to perhaps guess that it's not going to work is that products and co-products are sort of being lifted up to the tensor product structure by the adjunction that we've got. But you can never have a braided product or co-product. You could use the product to give you a symmetric monoidal structure. You could never use it to give you a braided monoidal structure. So maybe that's why, I don't know.
Okay, so that's fine.